35 participants, and hopefully more will be joining. So let me share my screen and then we'll start. Let me know when you guys can see my screen. Is it visible now?
Yes.
Good. So as Praveen gave some
Yes.
introduction about me, I'm Saurabh working at Intel Parallel Computing Lab at Bangalore, mainly working on parallel computing, performance optimization, compiler optimizations, and few related areas about HPC. And today we will be discussing mainly OpenMP as a parallel programming constructs or as a parallel programming tool, uh, which gives a very easy handle to write efficient and easy parallel programs. As the first lecture, Kalyan and Dr. Praveen discussed and showed the power of parallel programming with multiple examples with multi-threaded programs and how you can achieve the speed up by using number of multiple cores. So continuing from that context, uh, you can see the parallel programming is a practice of executing multiple tasks simultaneously, basically to improve the performance. The goal of this exercise is towards getting the better performance in terms of maybe the runtime or execution time, where the traditional sequential programs were not meant to run on multiple CPUs. So they are inefficient on modern processor where we have multiple cores sitting on single system. So it is becoming more important in today's world where multi-core systems are the de facto systems available for us. Even our mobiles and laptops are also multi-core systems these days. So there are different paradigms where parallel programming can be viewed. Multiprocessing is very popular and old way of achieving parallelism. So in system, there are always multiple applications running in parallel. Or if you say in Linux, you are suppose running multiple scripts or multiple applications simultaneously. So they can run independently, but they are not uh, kind of doing some common work together. So that can be some separate class of parallel programming. The one which we are currently interested in is multi-threading, which can be leveraged through pthreads, the one OpenMP which we will be discussing, Java multi-threading which Dr. Praveen showed you in the first lecture. And there is another class of parallel programming which comes from the distributed computing. Distributed computing as in when you have multiple systems, like not only multi-core, but multiple systems sitting together and they are doing some common job together by sending messages to each other. There are some famous MPI platforms to write the code, or Apache Spark is very handy distributed computing platform. So in this paradigm of parallel programming, we'll be focusing on multi-threading, mainly shared memory multi-threading with OpenMP. The key idea of OpenMP is why we should learn OpenMP. The first is very simple. It is very popular, and all HPC work, including if you say NASA parallel benchmarks or many scientific simulations, the source code are parallelized using OpenMP. The main reason for this, they are very easy to learn, and without uh, changing a lot of code design, you can still achieve parallelism. So you need a very minimal changes to code to achieve the parallelism. OpenMP has been defined, or at least you can be viewed as the set of compiler directives and the runtime routine APIs where you can use them in a certain way that it creates multiple threads, accomplish the job, and then finally hand it over the control to the master thread. We'll see all of these things when we go along. So to start with the today's discussion, I would assume that everyone has some introduction of C or CPB. May not be as complex as classes constructs, but just some for loop, variable declarations, and so on. And also, I assume that you are new to parallel programming. So if some of you have already got introduced to parallel programming, maybe few things may look redundant to you, few basic constructs and all. So please bear with me because I will be covering from scratch so that no one is left out in the understanding. Cool. So as I said, they are OpenMP is provided as part of interfaces that programmer can use without worrying about the low-level details of thread creation, thread management, or even low level synchronization among threads. So the constructs hides the details from you and just give the APIs or uh, constructs. It is a shared memory multi-threading model. Shared memory means your cores or your multi-core systems, they have a common main memory, I would say the RAM, common to all, accessible to all cores, and their L3 cache is also common to all. And when you run a multi-threaded program in OpenMP, it uses the common shared addressable space so that multiple threads can access the same set of memory locations. OpenMP supports C, CPP, Fortran, and widely used in scientific and high performance computing applications. So how they are placed in the total system? The stack of OpenMP looks like the first user level, where you have the application which you are say writing OpenMP program, and the end user who is using those as a just user of the application. The second level, when a programmer wants to write a parallel program, there are a set of OpenMP directives, the compiler which understands the directives and compiles the code for multithreading, the OpenMP libraries, and there are a set of runtime environments where you can specify certain configurations to OpenMP. And after the programming layer, there are runtime OpenMP libraries which directly communicates with operating system, which manages the thread allocation, how thread should get scheduled on actual hardware. And so all of those operating system constructs are sitting below OpenMP runtime and can directly communicate with hardware. So if you can see here at the bottom, uh, we are having, say, let me put laser pointer, or four cores as a hardware and common shared memory around it. And OS can communicate with those things on behalf of the high level programming interfaces like OpenMP directives or the runtime libraries. I would like to emphasize one point here that may be the confusion for many of you, maybe or may not be, that the threads which we create at application layer, thread means the independent stream of execution. The number of threads are independent of the number of cores sitting at the lowest level of hardware. So it may be possible that the application is, for example, creating 16 threads, but you only have 4 hardware cores. So OpenMP runtime will convert that code into low-level implementations, and OS will be taking care of scheduling those threads on particular processors. So maybe first 4 will be on P1, for second 4 on P2, and so on. The scheduling policy OS decides, and also up to some extent, we as a programmer or end user have control on it through some system calls or the environments which we can provide at OpenMP. So do let me know if you have any questions, and I would like to keep this session as more of interactive because that will be like we all can learn together and everyone will get benefited. So these are important concepts to understand before starting our discussion in details. Okay, so OpenMP constructs. For example, if you read this line, hash pragma OMP construct, this is the one, this is the way we provide OpenMP pragmas, hash pragma OpenMP and some construct name. And when you specify some construct, they are applied on a structured block of code. Structured block as in, if you specify a block of code in braces, it defines a structured block which executed one instruction at a time in a sequential order. So let's get started. Hello world. Whenever we learn any new language, we have to stick to hello world because it doesn't leave the world ever. So simple CPP program, hash include iostream, int main, some variable ID, and we are printing hello, uh, the ID, and world ID. Fine. And you compile this code using G++ GCC compiler, hello world hyphen O binary. If you run this program, you will get the output hello 0 world 0 because the ID which we have specified is 0. A simple CCPP hello world program with 2 printf statements. Now, this is your first Hello World parallel program using OpenMP. So I have added one header file, omp.h. Then I have written something in hash pragma omp parallel. Then I have written some function call which returns the current thread ID, and then followed by two printf statements, same as the sequential code. And for now, just bear with me. What are these things we will discuss? But if you compile this code with GCC and provide a flag f openmp and then binary name and run this program, you will get something output something like this: hello 0, world 0, hello 1, hello 2, world 1, something in a random order. Okay, so what basically happening? So this is a parallel program which is creating multiple threads and printing some output in certain or even random order. So let's take a keen look at it. The hash pragma, the hash include omp.h is a header file which understands the constructs from OpenMP, and the API's implementations are there in it. Hash pragma parallel is a parallel construct which defines a parallel region. So whenever we use parallel construct, whatever is included in these two braces becomes a parallel region. Okay, and within that region, there are multiple threads get created. So after this, there are multiple threads entering into this region and executing each of these statements in parallel. And this function call returns, which is a library function call, returns the thread ID. OMP get thread number basically. And you are printing two things here. And because of that, you are getting the output in the certain random order, because we cannot ensure that which thread is printing what. So maybe thread 1 is printing first and then thread second is also printing, and then so on. So this order, no one can guarantee. That depends on run to run variations. And the flag which we have given for compilation is used for compiling OpenMP program. If we do not provide this flag and still use the same function, the pragmas which we have defined, they are simply get ignored by the compiler. So this OpenMP flag is very important to basically create a binary which is multi-threaded. One more thing to emphasize here: when we create multiple threads at hash pragma parallel, at the end of this parallel region, all threads waits till everyone is reaching to this point. So basically, it is a implicit barrier point where all threads uh, arrive, and then only it exits the parallel block. So from main to hash pragma, there is only one single master thread running. Say thread ID is 0. Then inside the hash pragma parallel, there are multiple threads got created. At this point, all parallel threads waited till everyone finishes, and then again after that, only single master thread proceeded further from this point. Any doubts, confusion in this? Feel free to just jump in. I don't know whether I am able to see the chats. If there are any questions, let me check. Okay, there are. Is OpenMP specific to CPP or Python users can also use it? Okay, so Python that doesn't support OpenMP, but Python is very peculiar because there are many extensions to Python, and you can also write CPP extensions to Python. So you may have some function called uh, say parallel print at Python level, but at the backend you can have implementation which is CPP and OpenMP based. So if you want to achieve parallelism in that, you can use CCPP extensions to Python. Does it answer? Can you once again repeat the master thread? Okay. So master thread means whenever we have a sequential program, so one I would say one thread which is starting from main to end, that is a sequential single thread, which we have done since ages in sequential program. So when we say that this program is parallel, so multiple threads have not created till you invoke the hash pragma parallel, and only after that you have basically created multiple threads and then exited from that. Does that answer? Okay. You can also unmute and ask questions if there are any specific questions. Maybe because going back to chat and then reading it may not be efficient way. So we can be interactive and please unmute and ask questions.
And how many threads are there in this?
So that will come. That will come in the next slide.
Okay, okay.
Uh, so maybe why wait? Okay, as you
Uh,
asked.
yes, sir. Actually, this is Anantaraman. So I am just compiling that code, but I am getting some error. C++ level programming.cpp -f OpenMP, but I installed OpenMP also. But
Okay.
I'm getting error like cannot find no such file or directory.
Uh, which file you are providing, or like hello world dot same program or
Ah,
something else?
same program, same program.
So which compiler you are using?
G++
GCC or
or
G++?
GCC. Should I use GCC?
Actually, not a difference. So I guess there are slight differences among different compilers. Some
Okay.
compiler also accepts, uh, I think L OpenMP
Okay,
and
I'm
or some.
using Ubuntu machine.
Yes, so I can actually show you the
Okay.
demo as well. So for example, let me know when you can see.
Yeah.
So I have these programs, right? So G++, say py.cpp hyphen f openmp and any file, say my binary file. So it compiles. So
Okay.
my GCC version is
Okay. Okay. I think I forgot to that hyphen O. I forgot. Okay. Now it is compiling for me. Okay.
okay.
Hyphen O. I forgot. Yeah.
Yeah, hyphen O. If you do not provide this, it just creates the default binary name a dot out. It is just
Okay.
the name of output file.
Okay. Okay. But
So it will
okay.
be a dot out.
Okay. Okay. Fine.
Okay. Yeah. So you can proceed further.
Sure,
Great.
Yes,
sir.
sir. Yeah.
So as question asked, how many threads got created, right? Mm, yeah. So basically, there is OpenMP environment, OMP num threads. So whatever number of threads are by default specified in this, they are used by default by OMP parallel region. And you can also change that by this statement: export OMP num threads to any number, say 8, 16, 24, and these will get used by default. So if you do not specify anything here in parallel, so they are the one which are getting used. You can override this variable by explicitly invoking a function called OMP set num threads. If you use OMP set num threads by 8, whatever value you set here, they will get overridden by this value for this program. Other OMP programs will still be using the default value, but for this one, you will be using 8. You can also control number of threads per parallel region. So you may have multiple parallel regions, one after the other, and you want to control number of threads for a certain region. So you can specify number of threads along with the parallel construct as well. So if you use hash pragma OMP parallel with num threads 4, then for this block you will be using only 4 threads, although you have 8 threads in your OMP environment. So it uses default value, and you can also specify num threads using multiple ways, like either set it inside program or control it through constructs and so on. So whatever you specify, that becomes your team of threads for this particular parallel region, right? And if you want to view how this OMP parallelism works, it's like a one master thread starts from starting, and then wherever you specify any parallel construct, multiple threads got created. Again, you finish your execution of parallel region, run something in a single multi-threaded, sorry, single sequential master thread, and then again do something and so on. This is called as fork join. So because at this point you are forking multiple threads, then at the end of parallel region you are joining them and repeating the same thing. So they are fork join parallelism used in OpenMP.
Hello,
Now,
sir.
yeah.
Sir, in the previous slide, like the slide before this,
Mhm.
like the particular line export OMP num threads equal to 8. Where
Mhm.
should I write this in, like in the code? Like
No,
above
it should not
pragma.
be. It should not be in code. It should be from the terminal. So, for example, uh, as I showed here, right? So this is the Linux terminal Ubuntu, and if you say export OMP num threads equal to 16. So this is the way you write it.
And then I should do GCC plus and G++.
You don't need to even recompile the code. So whatever code you have compiled, it will just run as it is. So this is
Okay.
the environment set from the uh, OpenMP environment itself. So that's the beauty of this export, that you don't need to recompile the code. It just uses the default value. So if you have not specified these things, so again going back to first slide, here it will be like 16 threads running without changing anything. If you
Okay.
control from outside, specify 8, only 8 thread will be running inside.
Okay.
So that export is not part of code. It's declared as an environment outside the program.
So if I don't write that export line, then it will automatically take a 16 more like threads.
Yes. It will automatically take 16.
Okay. Thank you.
Yeah. So again, so as I mentioned earlier, OpenMP is a shared memory programming model. So what does that exactly mean? So consider this program where I have defined array int of size 10k, and again hash pragma OMP with 4 number of threads. And what I'm trying to do is I'm fetching my thread ID, and just randomly by some dummy operation I am accessing the idth maybe ith entry of A, and then storing it into B, and then finally printing it as the value of B. So when I enter this parallel region, all threads which are say 1, 2, 3, 4 all have access to array A, and they can read the value in parallel and they can save it to B. So A is basically shared among all threads. And as I mentioned in my first couple of slides, the shared memory is managed by operating system as part of the common address space among multiple threads. So as an OpenMP user, we don't need to worry about what is happening at the backend from OS, but just need to understand what variables are shared and what are not. So this variable is appearing before our parallel region. So this is shared among all. But when we have int b, that copy of int b is kind of replicated for each thread, and they are private to the execution of that particular thread. Another example of sharing where instead of only a, I have also specified b as a shared variable, and repeating the same exercise and writing this value a of id to b. And now I'm trying to print b. Here, if you mm, uh, think that a and b both are shared, reading to A is fine, but when I'm trying to write to B, all threads have single copy of B and everyone is trying to write to this value B. So as a standard of OpenMP and C++, we cannot guarantee what is the value of B because everyone is trying to write. It may be A of 0, A of 1 to A of n number of threads, or it may be junk because multiple threads trying to write on the same location and it may mess up the data, and so the behavior is undefined. And this also called as concurrent update to be because of multiple writes as a race condition or data race. So these things are undesirable in parallel programming unless you really want it. So these things, although you are having sharing, but they are not desirable sharing. So whenever we write a program, we need to take care of these things. But as of now, not to worry about this. Just understand this is how we share the memory across multiple threads. Fine.
So
Just all, Mhm.
the
Yeah.
previous. Uh, Sir, here in the first example, where inside the pragma OMP we have declared int b, so that
Mhm.
means we have four copies of int b, like four different variables, b1, b2,
No,
b3, b4, like that.
it's not like that. So basically, this is an independent execution of that thread. So whenever you entered this, so I don't know whether you understand the concept of heap and stack. So the
100.
execution of these statements go into the stack. So so these are different copies. So they don't share that stack address space together.
Oh,
So
okay. So there are
they
two
are
different
independent
address space.
executions. It is just like you are calling same function multiple times, and a variable is redefined inside the function definition.
Okay, okay, okay. Got it, sir.
Yeah, and here it is shared because these data will be shared among threads by OpenMP standards, and it will have a single copy. So everyone will be writing to its own, like the common copy of it.
Got it, sir. Thank you.
Yeah. Yeah. So now, as I mentioned, how do we know that what is shared and what is private to the thread? So most variables are by default shared, and the global variables which we define as CCPP, they are also shared. Dynamically allocated memory like malloc or calloc, they are also shared among all threads. And variables declared outside parallel for. So although these variables may not be global variables, but they are declared before parallel for in the scope of master thread. They are also by default treated as a shared variables. And there is an exception to it. There is another clause in OpenMP like OMP task, which we will visit some later point of time. So in only in this, the data is shared, like the data declared before this parallel clause is treated private. Otherwise, all other clauses treat this data as a shared data. Also, if some variable is declared in a uh, master thread scope, we can force it to be treated as a private data by using these clauses. So if you are writing, so here we will follow the default behavior as per these rules. But if you specify explicitly that A is shared and B is private, and then you still run this code without specifying int B, uh, you will be uh, executing the same stuff as you use the int B here as a private. So yeah, so I expect some doubts in this. So please feel free to unmute and ask.
Sir, in this second case,
Mhm.
hello. So
Yeah.
in the second case, when you say so this B is private, private is B. So
Mhm.
only the part of B is kind of getting executed in every thread. Is that something that is happening?
No, nothing part of B. So let me first explain. So whenever you have defined something like this, B equal to 150, and you specify private as a B. So OpenMP internally what it treats this variable as a private and creates a new copy of B. So you can say int B1 basically int B1 and then reads it and then writes the value of this current copy of B for that thread and then finishes the task. And that's why I kept it one more printf after this. So although maybe A0 is writing some 10 value, A1 is writing 20 value, the any execution of this part will not have any effect on the value of B. If you print B here, it will be again 150. So it's a basically new copy of B for this parallel execution.
Basically, this will output like value of B at thread one is some
Huh.
B1 and 2, and for the outside part it will be just 150.
Yes.
And
Yeah. Okay. So
So,
now we
sir,
have yeah.
so when we say that variables declared outside of parallel region are shared among the threads, so
Yes.
there's a difference between the master thread and the parallel threads, I'm assuming.
Yes. There's a difference between master and parallel thread. Although whenever you enter the parallel region, master thread also takes part in that. So whenever you say that num threads is 4. So ideally, when you print some OMP get thread number of like thread ID before this parallel region, you will get thread ID 0. Okay, as a ID of master is 0, and when you print inside, you will also get 0, 1, 2, 3, 4, 4. So master thread also participate in parallel region, but it has its own scope before and after the parallel region.
Okay, understood.
Yeah. So basically, it doesn't sit idle. That is the key thing to take away here. So there aren't 5 threads. There are only 4 threads. Master is common between master and the parallel execution. Okay.
Yeah, okay.
So far we have just discussed the dummy examples. So you may feel that what are we doing with the printing multiple printfs? So let's solve some real problem. So go back to your schooling of 10th, 12th, where we used to write pen paper exercise of calculating pi with numerical integration values. I hope you all remember what is pi and how to calculate that. Basically, it's a function f of x equal to 4 by 1 plus x square, and every point on this curve is defined by this function. And if you take sum of all these values as an uh, integration, you get a value of pi. And to calculate this analog function in a digital format or like discrete format, you stride the curve into multiple small deltas. Basically, it's from 0 to 1, and there are different strides. And you take the midpoint of each of the stride and calculate the volume of this rectangle. So for each of this rectangle, if you keep on summing up, eventually you will get the final answer is a value of pi. More number of rectangles you have, better accuracy you have, because you will be filling better details on the curve of an analog curve. Yeah. So let's solve this problem with general C++. Uh, okay. So simple sequential implementation. Okay. So we are defining some number of steps as the number of strides in this curve fitting, and this delta x is the basically the size of one stride. So out of this 0 to 1, maybe 0.01, which we will calculate, and just created some two variables x and pi defined to 0, and delta x is basically 1 by number of steps. So if you have 0 to 1 and 10 strides, which is 1 by 10 is your width of this rectangle, which is delta of x. And now you are iterating over each of this rectangle and calculating its basically area. So x calculates with this formula the midpoint of each stride. Basically, at 0th stride, 0 plus 0.5 into the stride gives you x, and then f of x is equal to 4 by 1 plus x square, the same formula I'm implementing. So these two are like irrelevant for the discussion, but just one function of basically x. And then you are adding this f of x to pi iteratively and finally getting the value of pi. Is solution problem clear to everyone? Because we'll be building many things on top of this problem. So I'll stop for a few seconds to like everyone should digest the problem and the solution in C sequential program. And if you have doubts, please unmute and ask. Water. Okay. So if you understood the problem, how can we parallelize this problem? Because we just are calculating the area of this rectangle, and we have some n number of such rectangles, basically number of steps. And because sum is operation which you can actually, it's like basically a commutative operation. So if you have say 2 threads, half of a rectangles can be computed by thread 1, other half can be from thread 2, and then finally you add the two areas to find the uh, final pi. So basically you compute a partial pi1 pi2's sum and then finally add. So that is one approach of multi-threading. So basically Suppose you have different stride and you have say 4 workers. Worker means threads, and each thread is calculating the area of one rectangle, and so on. And suppose you have multiple such strides, more than 4. Suppose you have how many, some 24 when 28 strides and 4 threads. So thread 1, stride 1, thread 2, stride 2, thread 3, and thread 4. And then again you repeat in second iteration uh, the same order: thread 0, thread 1, thread 2, thread 3, and so on. And out of these all strides or iterations, say thread 1 is executing uh, 0th stride, 4th stride, 8th stride, 12th stride, and so on. Similarly, thread 2, which is in different color, is executing second rectangle, then 5th, then 9th, and so on. They're index 0, so that's why starting from 0. Clear enough? The, the approach of parallelizing it?
Yes, sir.
Basically, we will be parallelizing this thing by fourfold. So one stride of this is getting executed in parallel instead of single. Okay, so now pay keen attention on the solution, everyone. What all we are doing to get this? This is sequential program. This is a parallel program. I have specified same thing, number of steps, delta is sequential, and I'm just considering that I am using maximum 100 threads in my system. It can be any high value, but say 100, and I'm creating an array of that size, so that for each thread I will be maintaining the local sum in that particular array index. So sum of 0 will be pointing to the sum of thread 0, sum 1 of thread 1, and so on. And again, same of sequential, we have delta computed similar to this, and we start a parallel region. So after parallel region, basically what we need to do, we need to write a function given a thread ID 0, what all iterations I would be executing. Suppose I specify thread 0 and I know that I have 4 threads, then next thread when I want to execute after finishing 0th will be 0 plus 4. So 4. Once I finish 4, I will be doing 4 plus 4, then 8. So this is a kind of round robin scheduling of stride to thread mapping. And we'll be implementing same thing inside this. I'm fetching my thread ID from OMP get thread number. Now I'm introducing another API from OpenMP, that's OMP get num threads, which will be giving number of threads running in this parallel region. Basically in our example, say 4. And then this statement just differ for now. And then we will be writing this for loop in a different way. For example, we were having from 0 to number of steps and incrementing by 1. Instead of that, we will be starting from your thread ID. Again, going back to this thread. So if you are 0, start from 0, 1 will start from 1, say 3 will start from 3. And then you are running one iterations and fetching next iteration by adding number of threads. Number of thread means say 4, 0 plus 4, 4. So this loop is getting incremented by that offset instead of plus plus. And again, we are exactly doing same operation of x and f of x. And instead of writing to a direct variable pi, I'm maintaining my temporary sum into the array of my index. So sum of index will maintain my local sum across all iterations. And this loop will get executed by all threads independently, starting from different indexes and maintaining different sums on their respective locations. Okay. And finally, when we come out, we want to sum all of these partial sums to get a final value of pi. Now let's go back to the statement which I deferred. We are maintaining the number of threads which were there in the parallel region. Please pay attention to this, what I'm saying. I'm maintaining number of threads which were created in parallel region, and after the parallel region, I am using that variable which I got as a number of threads outside this parallel region. Because after once I come out of this parallel region, I don't have any information of how many threads were created. So you cannot hard code this by setting some value. So programmatically you want to fetch it. It will be we have to maintain that value as part of for loop. But again, the same problem, right? The variable n threads I have declared as a shared variable because it is outside parallel for loop, and I want this to be visible outside parallel loop again. And if I don't use this if id equal to 0 and just use this number of thread equal to n threads, which is like fetching from the API, all threads will try to write to this variable, and I don't want that. That's why I am forcing only thread 0 to do that, and other threads should not execute this if condition. So only one thread will be maintaining this value, and then you basically sum it into final value of pi and then print it. So then it will have same execution as the sequential for loop. So that's how we implemented the uh, parallel version of the simple for loop. Now I'm open for questions. I hope there will be some questions.
Sir, for this
Yeah.
parallel version, so is this like we are giving some rectangles to some particular thread and some amount of
Yes.
rectangles to other thread, and then we are summing up?
Yes. Yes. The diagram which I showed, right? This diagram. So the different colors represent the strides computed by certain thread in this particular order. So thread 0, thread 1, thread 2, thread 3, and so on. So these are the stride IDs executed by thread 0, and the summation which maintained is the area of rectangle of these rectangles, 0th, 4th, 8th, and so on.
Okay. So we can kind of specify, right, sir, like if the thread is even, uh, if a thread is 0, then only calculate for the even strides, and if the thread is odd, calculate
Yes,
for the rest of the strides.
yes. So even odd will work for two threads.
Okay.
So if you want to use multiple threads, you can do something like mod operation also. Your thread. So basically, if you do some stride ID mod thread ID, if that is divisible by that number, so basically if you see T1, it is mod 4. So here mod 4 is 0, mod 4 is 1, and so on. So you can specify any strategy in this and can control your execution by mapping that strategy to thread ID. So once you know your thread ID, you should be knowing what is my set of stride to compute on or to operate on.
Sir,
Clear?
can you once, sir, can you explain like how would this thread, how would this execute for a single thread? Like, let's say we take ID 1.
Okay.
This.
Okay. So for ID 1, so once you enter this, ID 1 will start from here. Sum of, okay, there is a bug here. So this statement should be below this. ID is not visible here. It is only visible here. So let me fix that now itself. This should be after this. Okay. So you got your ID as a 1 because of from this API. Then you set sum of 1 is 0, and then you are not ID 0. Fine. Then you start from I equal to 1. Okay. Is I less than number of steps? Yes. Then you go inside this 1 plus 0.5, 1.5 into delta. So this becomes your midpoint of that stride. Okay, you compute this, and then you sum. You add this to sum of 1. Then you go to next iteration. 1 plus number of threads. How many number of threads are there? 4. 1 plus 4, 5. So I becomes 5, and then it becomes 5 plus 0.5. So the midpoint of fifth stride, you compute f of x, add it up. Next iteration of this, 5 plus 5 plus 4, 9. I becomes 9, midpoint of 9 stride, and so on. So once you finish all execution for thread 1, all strides with 1, 5, 9, 13, it will have the sum of those strides basically for only 1. So similarly, all threads will do their own sum of 0, sum of 1, and so on. Is it clear or still confusing?
Yes, sir. Yes, sir. Okay.
So, hello, sir.
Yeah.
So, in when you're defining int n threads, Like, where are you defining that in threads? But you are not
This one,
in. No, not this one. Like THREADS in threads.
this one.
Like you are not giving it any value.
Value as in you mean the initialize is to something.
Like in threads is the number of. Oh, sorry. Is it a variable that you're like?
It's just a variable. You can just put your name. So
And
it is just a variable. It
can
is
you
variable,
explain this
and you
line?
getting value from this API.
So can
Yeah,
you
which
please
line you are
explain
saying?
that?
This one?
No. Can you please explain that if statement?
This one.
Yes, yes.
Okay. So if you ignore the for loop and the way you want to add the final sum, you don't need this line. The purpose of this line is you want how many number of threads executed in parallel, and you can only get information using this API. OMP get number of threads inside this region. If you run this example, this API outside this, you will get the value 1 because master thread will have only single number of thread.
Yes, yes, yes.
But inside parallel, you know that there are 4 threads, and also you want to maintain this information. So you have one shared variable which is n threads. But even though you have shared variable which you want to maintain out of parallel for loop, you also don't want to everyone to write to that variable because otherwise it will mess up the data, right?
Okay.
So only one thread is writing, which is thread ID 0.
I can use any ID, thread ID, like if ID is
You can write any thread ID less than your n threads. Suppose there are 4 threads, you can use anything ID1, ID2, ID3. You can use any thread to maintain this information. Nothing
Okay.
fancy about thread 0, but ensuring that only one thread is writing to it.
Okay. Sir.
Clear?
And that when you define the maximum threads, like is that a new is this a function that you're defining?
It is a variable. It's not even.
Okay.
It's just a hash define. It's just wherever you encounter this thing, right? In CPP, compiler just replaces that with 100. It is not
Okay.
even a variable. It is just a placeholder.
Okay.
These are like standard way of C++ defining hash defined statements.
Okay. Sir.
You can also hard code this here. Sum of 100.
Okay.
Yeah.
So one follow-up question over here.
Mhm.
When we execute this function OMP get number of threads, what will the value will be here, 4 or 100?
Here
Yes, sir.
it is 4. This is just a variable. This is nothing. So this is not even OMP variable.
Okay, so then one doubt which I have is now if we have if we have 4 threads, okay,
Mhm.
then we'll be only using the sum array has 100, the sum array length is 100, right, sir?
Mhm.
But if we have 4 threads, so we'll be writing in only 4
Yes, only 4.
yes, but then we are summing it up for entire.
No,
Okay,
that's what we are maintaining it here, and then we are using that bound to limit your execution till only that point.
okay, got it. That bound is there. So can't we
That
define it?
that was the only purpose for that.
Okay, now I understood. So can't we specify it from the beginning itself, 4, 5, 10, how many we want?
You can, but it will be again hard coding, right?
Oh,
So
okay.
so if you don't want to limit your execution, so you have, suppose you write program for CPU for four cores, but tomorrow you want to run it on a cluster which has say 56 cores. So your program still should be able to use that parallelism.
Got
So
it,
you
got it.
don't want it hard coding basically.
Yeah. That bounding I was not understanding. I thought garbage value will come in and then the
Yeah,
sum would be correct, but that bound
yeah,
I.
we don't want that. Yeah,
Thank you.
yeah. Okay. So if everything is clear here, we can proceed
One more
further.
question, sir.
Yes.
Uh, is the underlying implementation of OpenMP is using pthread or it's completely different than pthread?
It is pthread.
It's pthread.
Yeah.
Hello, sir. Another question from me. In the sum array, it only only the array in the sum array only the array element from 0 to 3 is filled, and the rest all are empty, right?
Yes.
Okay.
Empty or unused basically. Yeah, they are empty.
So they'll have some garbage value, right? So they'll not be empty completely. Yeah.
Empty. I mean to say that they don't have any useful data. They are just sitting there with
Garbage.
garbage value. Yeah. That's why we are writing 0 to that ID to initialize that value here in the statement. Okay. So we can discuss more interesting topic if we have clear with the basic stuff. Now I want you to introduce some new thing which I think you may not have encountered, or if you encountered, well and good. What is the problem of using this fashion of maintaining the partial sum in terms of performance? So if I run this code, will I get the best possible performance from OpenMP or from any parallel program? So say pthreads. The answer is no, and the reason behind that is very subtle and peculiar about how the data is maintained in the address space or in the memory or in caches. So the problem uh, is famous and called as fault sharing. Suppose you have the sum array of size 8. What exactly happens? So this array allocates the consecutive 8 uh, allocations of starting from 0. Right. So and double is of size 8 bytes, and your L1 cache. So I hope you are aware of L1, L2, L3 caches, and L1 is the nearest cache to CPU, and the size of that cache is 64 bytes, and CPU only interacts with that level of cache. And when you declare this array, they are fitting into the size of one cache block. Okay, 64 by 8 is 8, so there are 8 elements in one single cache block. And when say thread 0 is writing its partial sum to that sum of 0 index, it will be writing to this location, the first location of this. Second thread will be writing to this location. So conceptually, if you see, there is no data race, there is a safe execution of shared data, but the block 0 present in the cache of both threads, say thread 0 and thread 1. And I don't want to go too details about these things, like they are very detailed cache coherence protocol, how they have been implemented, designed. So I just want to introduce you to the concept that if such thing happens, that your data is fitting in a single cache block and different parts of that are getting executed by multiple threads on different cores, basically they'll get sequentialized at cache block level. So this will write to this location. The complete block will get flushed to main memory like RAM, and again it will get bring back to the cache of thread this, and then you again write to it. So this introduces the sequential component to your writing, and you get the suboptimal performance. Clear or doubt? You may have doubts. Feel free to jump in.
So to make sure like this can be avoided by like not having the number of threads equal to that block size.
No, not number of threads. Number of threads can be anything. Number of threads can be 1,000. So if you are having some 16 threads and this layout, so only the threads which are operating on this 8 will be contending. 16 thread will be independent of this.
Okay.
But the threads which are operating on single cache block, they will introduce that sequential component into the performance.
Oh, so this will happen for any number of threads.
That can happen for any number of threads. There is nothing
Okay,
about number of threads. It is about the way you have defining the array.
Right.
So to avoid that, I was having the next slide. To avoid this fault sharing, you can do something called as padding. So instead of using one-dimensional array, you do two-dimensional array where you are having complete 8 elements as a block 1, cache 1, and then B1 after that, and only accessing the first column of it. So thread 1 will be operating on this cache block, only first one location, and other are wasted. Basically, just they are just padded up without any use, and so on, so that you don't have any fault sharing. And if you write your code in this fashion, you will get better performance than the one which we have implemented. So
Sir,
padding
but
helps in that.
this depends on the size of how much L L1 cache is bringing from outside.
It is not about how much L1 cache is bringing. It is about whenever you access this data. So this location, maybe not this location, this complete cache block must be there in your L1 because data travels in the chunk of blocks. So 64 byte at a time, this has to be there in your L1. So, so yeah, it's about the cache block, not how many cache blocks are there. So in this
So
case,
how much are we padding? Does this always be 7 by 7
uh,
number?
so I was coming to the next slide, but okay. So how much you want to pad? It depends on what is the data type. So suppose you use int, then int is size of 4 bytes. So instead of 8, you need to pad 16. Basically, you need to ensure that you are having 64 bytes of size cache block. If it is a character, then basically again you add all 64. So basically these are the 64 bytes. And
And so does this remain same for all types of L1 caches?
no, particularly for current CPUs, yes, but that's what I was coming to. So this solves the problem by padding this, and our program will change something like this. Your sum array will be of size 2d8. Wherever you have defined sum, it will be sum of 0, sum of 0, sum of 0, and so on. But padding requires deep understanding of what is the size of your cache block, what is the architecture you are working on, and if it changes, your program will not deliver same performance. And this is not a recommended best way to do that. So are there any better way to handle this type of problem? Can you avoid sequential loop at this? Because once we have executed all this, we also running the final pass to collect all sum. And if number of threads are very high, then you will have sequential component here as well. Although in this example, it's only one addition, but in real world applications, you may have some heavy computation going on in such loops. So
Can
try
we
to understand.
define a
Mhm.
local variable itself within the
Yes.
and then add onto that?
Yeah. So what it will require? So in current setup, what we are doing, we are computing the value locally and writing it to some shared store, which is shared to all and then visible outside the parallel form. Okay. Can I do something like all threads will go to the shared variable and add its own value the way we were doing in the sequential one? Can we still keep the pi as similar stuff and still add my current without maintaining multiple values as a array? So we can do that, but to do that we need some thread synchronization because we will be adding to the same location, right? So hold this problem for now at this padding moment, and we will revisit this once we cover the critical section part. Okay. So this new construct I am introducing to you now, hash pragma critical. What it ensures that suppose some dummy program where you have to maintain some result, creating multiple threads in parallel, getting the ID thread ID, and computing some f of I. Instead of pi, you can have any random function getting the value of b, and now you want to add that value to result. So if you use hash pragma OMP critical, till this computation of function, everything is shared. But once you hit this critical, only one thread at a time will enter to this part of code and execute it and then come out. So result value will get updated only by one thread at a time. Understood?
Yes, sir.
Okay. So can anyone tell me what is the problem with this? As I mentioned that critical construct ensures that only one thread enters into this. What is the problem with that? I have anyway written it here. The downside is sequential execution at a critical section because it will sequentializes the execution at this portion. So it has a huge impact on your performance. You are expecting that multiple threads will get executed in parallel. But for not even for single, every iteration you are executing in a critical section. And basically, we do not need uh, every iteration to be in critical. You can add all of them temporarily in a iteration and finally merge it uh, as in final value. For example, instead of writing it directly here inside a for loop, you first compute everything locally. You create new variable as a local result for that thread. You add it the way you are doing a sum of 0, sum of 1, right? So every thread had shared data, shared memory location. Instead of that, you have your local copy of that. There is no false sharing. There is no padding required. Single stack variable. You add your value, and once you come out of this for loop, after iterating over all, say, stride in our example, you only call the hash pragma critical at the end where you want to uh, write that. So this statement is still inside the parallel for construct. So every thread will reach here and update the value one at a time, only n number of times, where n is number of threads. Understood? Any doubts in critical?
Sir, just to make sure, so the
Mhm.
local result, every thread will have its own copy, right? Like every thread will have own local result.
Yes, because it is defined inside the parallel for in this statement.
Ah, right, yes, okay.
Yeah.
So this critical is ensuring that every local result for that particular thread is getting summed up.
Yes.
Does
And
this also
no other thread is adding it into the arrays.
no other thread? I didn't get a second information.
So matlab, whenever we are adding one thread is adding this value to the result, it basically it is one after another, just like a for loop. Thread 0 is adding, thread 2 is adding, thread 3 is adding, not in particular order, but only one at a time.
So if ordering of my thread is mattered, where I need my 0 thread and after that I need thread 1. So this will do randomly. I think like
this will do randomly. Yes.
okay.
So if you really want the order, you yeah. If you really need some ordering, then you cannot do something like this because you cannot ensure that which thread will reach here. So what would you have done for that? That I will explain later because there are constructs to ensure that if you really need the order, but maybe once I introduce you to the other construct, we can maybe define that solution as well if time permits. Basically, the rough idea is you will ask all thread to wait here, and then you do some 0 to n. Uh, but there also you cannot do that because then you will lose the context of this local arrays. So you need to think through if you need that order intact. Maybe you may need to fall back to padding and all the other stuff. But if ordering matters, this solution won't work.
Sir, and also, sir, if the amount of job, let's say, so here for loop we are particularly adding these f of I, but let's say the job is like unequal or something like for every for loop, we have some different amount of tasks to do. Then so I think then also will this work, sir? Like
Yeah, different amount of. You mean like performance wise or correctness wise?
correctness wise, let's say simple example will like first thread is adding only 2 rectangles and let's say second thread is adding 4 or 5, and it is the variable of the rectangle amount adding up is getting different for every thread.
Yeah, but the function is sum of all, right? So whether you add a plus b then plus c or a then a plus b plus c. So ordering of summation doesn't matter. So this property of operations called as associative and commutative. So if operations are like that, then order doesn't matter. So you will get the correct output.
Thank you.
Clear, right?
Yes, sir. Thank you.
Okay. Another construct similar to critical but slightly different from that is atomic. It does exactly same thing, but critical is generic. You can have n number of statements in critical. You can have result plus something, printf, n number of statements. But atomic works on specific operations where It also ensures that only one thread at a time will execute this instruction, and it is supported by some operations which are binary operations like x plus 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 x, like here plus equal to, and so on. And the implementation wise, they are different. Critical is costlier than atomic because atomics are supported by the hardware instructions, which are atomic instructions supported by some of the hardwares. So OpenMP checks whether the atomic is provided, and if hardware supports that, it will use the instruction. Otherwise, it will fall back to critical. So this is similar construct, but slight different flavor in terms of performance and hardware support.
Sir, what do you mean by hardware support?
Hardware support means when we do some addition, right? So any plain addition. So you will have hardware instruction, something like add a comma b in your instruction set from say x86 you are using. So CPU itself will have hardware wired for it. So instruction is kind of hardware support. So adder, subtractor, you must have learned in your schoolings. All those adder, subtractor, comparator. These are actually circuits which are there in CPU. So if combinations of that supported by hardware, then that becomes single instruction. If there are multiple instructions are required, so for example, if you're doing addition, then subtraction, multiplication, there are 3 different instructions. It's not single instruction, right?
Yes.
So atomic is also single instruction, which ensures that you are loading data, you are writing to it, and you are storing it back. So without support of atomic instruction, there are 3 instructions. You are loading local value, you are adding it, and then you are storing it. 3 instructions. If you are atomic, then it's single short instruction. So yeah. Okay. So these are actually some background details of how atomics and how race conditions are introduced by these multiple instructions. But I'm keeping it more of towards the OpenMP construct level. So the programmer don't need to worry about the underlying implementation, but the more of construct level, how you can use that. But yeah, good to know that they are hardware instructions, not something else. Okay. So now I'm revisiting the example of pi calculation with atomics or with critical section. So we don't need this array. We don't need to maintain the total number of threads by keeping threaded 0 and something.
Saurabh,
And we just need to maintain the local. Yeah. Yeah, Varun.
I think we're supposed to give a break for around 5 to 10 minutes.
Yes. So I'll finish this slide, and then that's a good stopping point so that
Oh,
we'll finish
okay.
one topic, and then I was
Okay.
waiting for that. Yeah. Thanks for reminding. Yeah. So we don't need any instructions. We just maintain local sum. We add it here, and only after your for loop ends, you just do OMP critical and then add your value to pi using critical and then print it. So similar program which we implemented with some padding, without padding, can be implemented with simple OMP critical uh, sections by ensuring no data races. Okay, so now so far we have seen the basics of OpenMP, shared and private variables, the implicit barriers at the end of parallel for loop. After barrier, master thread takes the hold of execution. How to get number of threads, how to set number of threads, how fork join and works, what is critical atomics. And next we will be covering the very important and very popular construct like OpenMP parallel fors, sections and tasks. All of these are kind of siblings, but out of this maybe parallel for got more popularity. So after this break, maybe we will just quickly jump into parallel for and cover the rest of these things. So we can now take a break for a few minutes. If
Small
anyone
question
has
there.
any question,
So I have a small
we
question
can
there.
have.
What was the reason
Yeah.
behind choosing round robin method? Why can't we just take first thread processes the first 4, the next thread processes the next 4? next thread process the
There
next.
was no actually reason. You can do any mapping. So if you use first for next thread, second to next thread, that is also possible. So to introduce complexity in the answer, I kept it like that, so that your
Yeah.
problem may not be always reducible to consecutive chunks. You may need to define some functions from your thread ID can map to your problem instance. So no reason, single liner. You can distribute by
Got
any strategy.
it, sir. And does that has any impact? Like maybe last class we studied about cache miss and cache hit, right? So the style the way we choose, does that has any impact on cache miss and cache hit?
Yes. So the way I showed, right? Uh, False sharing. So in that example, if
Hmm?
you are having the eight threads operating on 8 different strides, then your sum array will have the false sharing problem. But if you are having, like, say, one thread is doing all first eight, then second thread is all second eight, then you don't have false sharing. So in that aspect, having those consecutive chunks to single thread is beneficial. So they will have impact on the performance.
Okay. Got it. So if we do that first four, then the way you showed us someone, we can do
Mhm.
that way. There will be no problem of false sharing, right?
Yes, we will not have any problem of false sharing.
Okay.
Yes.
Got it, sir. Thank you.
The examples are designed to introduce more concepts. That's it.
That is understandable, sir. Thank you.
Yeah. And there are questions on chat. What kind of setup I do need to practice this on Mac OS? Okay. So actually, Mac OS has LLVM GCC compiler. So it doesn't support directly doesn't support OpenMP. So you can install with Homebrew GCC that supports FOpenMP as well. So yeah, if that answers, you can just Google it. So you may find some setup how to do out on Mac OS. It works basically. Is there limitation on number of threads for per processor, like limit of 2 processor per core? Okay, so number of threads are independent of number of processors on system. So suppose you have a CPU of 4 cores, say hyper-threaded to 8 cores, you can create any number of threads, 16, 32, 64, and the limit is designed by operating system, how many software threads you can create, and the strategy of scheduling those threads on CPU is the job of operating system. So no limit of creating number of software threads or OpenMP threads. Does that answer, Subramanian? But also note here that if you create multiple threads, it will have some implications on performance. As Dr. Kalyan also discussed yesterday and showed you the example, if you keep on increasing multiple threads, it has implications on performance. Okay, threads per core versus OpenMP threads. This is very important concept. If anyone has missed out on, I'm repeating. Threads per core is actual CPUs. Basically, let me show you on this. So if I do LS CPU, this has 8 cores, but what it is saying, cores per socket is 4. So this means there are basically 4 cores, 4 CPUs, and each CPU has 2 hyperthreadings, and this hyperthreading is independent of your OpenMP threads. So, and basically, um, they are logical partitions of single CPU. So these are basically, if you consider this as a number of CPUs, 8. Say you can say CPU 0 to 7. So these are kind of actual physical CPU sitting on your hardware or whatever, say Intel or AMD, whatever CPU you are using, they are real CPUs. But when you say OpenMP threads, they are software entities. So you may have thread 1 to thread 100, and when they are running on the CPU, they are running on only one of those 0 to 7 because there are only 7. That is the difference between threads per core and OpenMP threads are independent of it. Does that answer, Anand Raman? This is actually a very important difference to note. So you should not have any confusion after this. I'll just take break of few minutes. I'll just have some water. Let's start. Okay. So let's jump in. So just want to have some terms which typically used in parallel programming. SPMD versus work sharing. SPMD is the one we just saw, right? Single program, multiple data, where multiple threads are operating on different part of the problem, and we
Sir,
finally getting the output.
no
Yeah.
screen is showing. Okay, so now it's
Is it?
yeah, now it's showing.
Okay. Visible now?
Yes.
Okay. Yeah. And the way we divided our problem manually to map thread ID to and the piece of the problem statement, right? As one someone suggested also, can we do something different? Can we give first chunk of task to thread one, then second to second? But in this way, we have manually divided task. We can do any random shuffling of tasks. Instead of that, OpenMP provides standard constructs, which are work sharing constructs for parallel for tasks and sessions. We'll see each one of them one by one. So basically parallel for loop, very popular one. Consider you have a problem of vector addition where you have a three arrays A, B and C and vector A plus B equal to vector C. Very plain for loop of 1000 iterations. And you want to add element by element the sum of these two into the respective things. So earlier we would have again done same thing. We would have started parallel for, then get thread ID, and then assign those uh, offsets. Instead of that, OpenMP just provides single thing. You create a parallel region, same as earlier, and just write hash pragma for hash pragma OMP for. And internally, it will take care of everything. It will take care of thread creation. It will take care of the distribution of the loop iterations equally among all threads, and it will get the output of A plus B equal to C into the final array. This can also be done in a shorthand fashion. You can also specify instead of two layer of hash parallel and for, you can write in a single line pragma OMP parallel for. Very simple, right? Straightforward. No fancy stuff. This is just one statement executed by all threads in parallel. So if you implement this, that's much. You have a parallel program running with for loop parallelize across multiple threads. One thing to note here, after you finish parallel for, so whenever, for example, this earlier we saw that all threads will wait at the end of parallel region, right? Before they enter into master thread. But in such constructs where we have OMP for, after the for loop ends, all threads wait at the end of parallel for boundary before entering into the other part of parallel region where they may be parallelism or not, but they wait at this point. So there is a implicit barrier at the end of OMP4. Clear? So to use this construct, although it looks very simple, one liner to add, it also adds some responsibility to us. Whenever we are adding such things to our sequential program to parallelize, you have to ensure that there are no loop carrying dependencies. For example, if your expression is something like that, C of I equal to A plus B multiplied by C of I minus 1. Basically, so suppose you are at one iteration and you want the value from the previous iteration. In this case, you cannot execute those iterations in parallel. So you need to ensure that your for loop body doesn't have such expressions and ensure that they are data independent. And there should not be any undesirable sharing of data, the way we have seen in our Pi example, where multiple threads are writing to a single variable. So if such things are there, you cannot use directly OpenMP parallel for. And if you use it, it will behave in an unpredictable way. It will give you wrong output, or even your program can crash. So to highlight that, I am again repeating that the responsibility of ensuring that your loop is parallelizable is on programmer. Sure. So another construct I would like to introduce here, that is reduction. Very important construct, and which can solve many of our problem and burden from programmer to uh, basically maintain the thread synchronizations. Suppose you have an array and you want to sum the array into a final variable. So you can do something like that, parallel for reduction, and then specify the operator plus operator for variable sum, and it will basically run all these things in parallel and add the a of I to variable sum by multiple parallel executions. So you may feel that this is exactly same as the critical section, but it is not. When you provide this reduction operation, it doesn't add one after another by each iteration. Basically, what it does, out of these 1000 iterations, suppose you have 10 threads, each thread will execute 100 iterations of this for loop for simplicity, and it will maintain their own local copy of those 100, and then it will finally reduce it to 1 by like tree like structure. So you have a first layer of partial sums, then you again, let me see if I can use pen. So basically what will happen, suppose you have two how many threads, 1 2 3, some thread. So this thread is creating this sum, this creating this sum, and so on. Okay, so you have this layer of sums available for addition. Then what will happen, it will do something like this kind of barrier, and it will add these two in parallel. And if you have again, we will have something like this as well, no? And finally it will add something like this, and eventually you have value 1. So you will have parallel executions across all iterations, and the sum is also getting added in parallel with this reduction fashion. So this construct will take care of all the underlying devils and just give a cleaner APIs to implement this logic. So internally what it does, it creates local copy of the variable which you provide for reduction, update their local copy, and local copy is reduced to single value using this mechanism and stored into the original value, which is the sum in our example. Any doubts in this?
Sir, is there a sync happening after every once we move from branch 1 to branch 2, branch 2 to branch 3 like that? Is there a sync happening?
This one you are saying?
Yeah, correct. The line which is that a sync operation?
This is sync operation. But OpenMP will do it internally. It will not have a global sync across all. Whatever you want to add, it will only have sync for those. Here sync for those, and then so on.
Okay. What it said.
Yeah. So it will do something like that. And the reduction is very effective. You don't have any sequential bottleneck as you want to add all 1000 elements separately. So it will take care of it.
Sir, for this reduction, can we also do operations like division, sir? Like
So reduction operations are only allowed when the operate. Maybe I might have the next slide. I don't know. So operations which are commutative and associative. So when the order doesn't matter, the final output of the answer, only those operators are supported by reduction. All operators are not supported by reduction. So if you just try to search for operator supported by reduction by OpenMP, you will get a list of operations. Division doesn't support it, right? Division is not
Yes.
associative, so you cannot use that as a reduction.
Sir, the
But
plus
for
symbol
the
after the word reduction in your sum, just beside the sum, is
Mhm.
it a syntax or
It is a syntax. So this is a keyword
okay?
reduction. Then you specify your operator which you want to reduce, and you also ensure that this is the reduction operation. Here it is common between both, and the variable on which you want to reduce. So the sum variable which was specified globally, you use same variable here, and you can reduce.
Okay, sir. Okay, thank you.
So you may not be able to write a fancy complex expression here in the reduction. Before that, you can compute any f of x, but when you want to reduce it, it should be a simple operator which can be reducible. Fine. Any further questions? Okay. So now you will think why we did all the exercise for last 1 hour or pi example, and why didn't I just introduce this syntax, right? So again, I'm revisiting pi example. This was the first code which we started with, sequential code. Like we have number of steps, and we want to do two parallel. So instead of that, I have just done, I have just added one liner here, hash pragma parallel for reduction with pi, where everything is exactly same. You are not changing even this line, they are same. You are not even changing this line, and nothing is changing as it is. Only one single liner OpenMP construct can convert your sequential code to the most efficient parallel one. So that's how the beauty of OpenMP. With very shorthand expressions, you can convert your sequential program to parallel one. Of course, by ensuring the correctness and all, that is up to programmer. I hope everyone now appreciates whatever we discussed so far. The complex statement, critical, fault sharing, all these things are just taken care by just one liner construct of OpenMP. I hope everyone is convinced that this will report a correct output.
Yeah, I have one doubt here, sir.
Mhm.
The last slide when you were showing the reduction operation, there was an array over which we did the reduction, array A, right?
Mhm.
So in the next case also, do the pi variable in the next slide, the example which you're showing, the pi
Here,
is not
here we did not
there.
do reduction on A of I. We did on sum.
Oh,
So we are summing. So we are adding value of A of I to sum. We want to add all of these elements into one. So we are not reducing the A. We are reducing on sum. So you can have any
got
expression
it,
of,
got
you are having any expression of A of I. It doesn't matter. That is just a value you want
okay,
to reduce. So here also
understandable.
you are computing f of x by whichever formula, and then you are just adding that final value to pi. So you are reducing on pi.
Hmm.
Correct?
Yes, sir.
Yeah. Now the important and very important thing to discuss in parallel for, as someone also said, right, which iterations are executed by which thread. So that is controlled by the scheduling policy of OpenMP, and which is mainly required for load balancing purpose. Suppose you have again the same loop where you are doing some regular operation, right? Just adding is like every thread will more or less spend same amount of time. But if there is some f of x which takes more time than f of y, where f of x and y are the iterations of for loop. So suppose you assign some task to thread 1 and thread 2 in certain way that only one thread is spending a lot of time and few threads are spending very less time. So in that case, you will have load imbalanced execution, and the total time of program will be bounded by the slowest thread, and that is defined by the scheduling policy. If you do not specify anything, the OpenMP will equally distribute the loop iterations and give first k iterations to thread 0, second k to thread 1, and so on. So all iterations are tied together in a chunk of k, where k can be defined by n by number of threads roughly. Let's see. So basically what I'm trying to say here, if we have something like this where number of iterations take something amount of time, okay, then something like this, then something are randomly high, randomly low. Pardon my bad designing on screen with mouse, but I think I want to convey the concept. And so if you do equal chunking, so this is like thread 0, thread 1. So you, suppose it takes some 5 seconds to this, to this, and 4 to this. You're bounded by 5 because all heavy lifting is done by single thread. Instead, if you have done thread 0 here, thread 1 here, thread 2 here, they would have distributed that task and they would have finished faster. So to do that, we have another construct called as schedule dynamic, where you specify that how many consecutive iterations one thread should execute. Suppose if I specify 2, thread 0 will take first 2 iterations, thread 1 will take second 2 iterations, and so on. Once these 2 finishes by thread 0, the next set of iterations will be picked dynamically by that thread, whichever finishes first. Right? So that whosoever finishes first will be doing more work, and whosoever are doing heavy lifting, they will continue doing their work, and other threads will finish the remaining task in a iteration. So that way you are doing dynamic scheduling. Guided scheduling is something different, which is like you initially start with some set of values, and OpenMP will gradually start decreasing number of iterations assigned to one thread. So you specify suppose like 10 iterations, then OpenMP will reduce in the next iteration to 7, 8, 5, and eventually you will reduce to 0 all threads. And schedule auto means OpenMP will decide what it want to do. It's not default equal chunking as statically. It is not dynamic specified by us. Based on its own experience and own heuristic, it will randomly, not randomly, it will with some strategy, it will schedule your threads to the number of iterations to different threads. These are different load balancing strategies using thread scheduling. And the syntax for this something like this: OMP parallel for schedule dynamic, and where you want to bind 4 iterations together. So this is important concept in parallel for. Any questions on this? Okay.
Number of iterations, we mean like I equal to 0 to 3 will go to one thread,
Yes.
and then 4 to 7 will go to the next, like that way.
Yes. Is it default?
Yeah.
Default, it will go that way. So if you specify dynamic, say 1, so it will be converted to the one we have seen in a Pi example initially, where every thread is just taking consecutive iterations and then going in a round robin way.
Okay, understood.
So basically, you can mimic static using dynamic as well by controlling the value of chunk size. If you specify chunk size equal to total iteration divided by number of threads, it will be converted to static.
Okay, thank you.
So again, summarize, we have seen in for loops, parallel, for, construct, reduction, and scheduling. Now let's visit the next important OpenMP construct, sections. So before going to sections, there are a few things to be understood in terms of synchronization. So now I'm introducing new construct from OpenMP, like called as barriers and no wait. So how do they work? So when I said after for loop, there is implicit barrier that all threads wait at that point. We can also explicitly add the barrier in our parallel region. So basically, this is a parallel region. having some shared and private data, and you want the thread ID to be captured here, perform some operations by all thread in parallel, so that A is populated completely, that A of 0, A of 1, A of 2, that A of array A is completely calculated by parallelly by multiple threads. But now when you want to do next operation of C of I, you want that whole A of I should be ready. So to ensure that, we need to also ensure that whenever we are entering this point, all threads should finish and reach to this point, right? So this can be ensured by OMP barrier. So this statement will not get executed till all threads in parallel region execute this big calculation one function call. Clear? Okay. So once the barrier hits, you have completely A calculated, then you again execute your OMP parallel for, execute this for loop in a OMP parallel for loop way, which whatever default scheduling policy, and then you move to the next for loop. That also you want to execute in parallel. This will anyway ensure that you have implicit barrier. So all threads are reaching here before starting this for loop. And once this for loop is start executing, I'm saying no wait. Why? Because the calculation 4 is independent of the outcome of B, right? So I don't need the value of B to calculate this statement. So once thread 0 finishes all of its iterations, it do not need to necessarily wait at this point to other threads to finish. It can just go ahead and run this function call. So this is controlled by no wait. If you do not use no wait, all threads will first reach this point and then only will execute this statement. So it will be unnecessary loss of uh, clock cycles and the performance. So this is the way we control the execution through barrier, through implicit barriers, and through no wait by allowing threads to just continue after you finish your task in parallel for. Clear? Or any doubts in parallel and barrier no waits?
Sir, one thing which is there, let's suppose if we have 10 threads, then
Mhm.
if we don't write no wait, then all 10 threads will be used to calculate B, right? But if we use no wait, then maybe 8 threads are used to calculate this and next 2 threads move ahead. Is it like this?
No, it is not like that. Suppose you have 10 threads, all 10 participate in OpenMP parallel for to calculate B of I here in this statement.
Okay.
And not all threads will finish in the exactly same time, right? Sometimes some will finish at 9 seconds, some finish at 8 seconds because of load imbalancing, right?
Mm-hmm.
So whenever they are finishing, they don't need to wait for other threads to finish. They can just execute their iteration and wait at this point.
Okay, okay, got it. That's very smart, actually.
Yes, that is very smart, and that offers you more parallelism where you don't need to unnecessarily wait.
Got it, sir.
Yeah.
Sir, we cannot use scheduling in such for loop, right? Where we are doing no wait.
We can. Why not?
Oh.
We can
Because
use
those threads
any.
have moved ahead, right? So like,
No,
how will they?
thread will not move ahead until it finishes its own chunk. So if scheduler is still scheduling task for yourself, then you are still doing the task for scheduler, right? So if you
Oh,
are,
okay, okay.
so once the scheduler says that okay, you don't have any work, all threads are doing their own work, and there is no new task to be assigned, then you are done basically. Then you continue.
Oh, okay, okay, understood.
Yeah. Any further doubt? Okay, so I assume that this is clear, and now we can move to uh, some more construct in synchronization, which is master. So remember we have our first version. Let me laser. I don't like this. So we have our first version of pi calculation where we have used this id equal to 0, where you wanted to just keep track of number of threads, right? So OpenMP also offers construct called as master, where you specify something do anything in parallel for. If you specify pragma OMP master, this code will be only executed by master thread, and other threads will just skip this part and continue with their own stuff. Right. So it is similar to critical, but only for one thread. So only one thread is entering here. Other threads are just skipping this part and reaching to barrier and doing other stuff. Okay. Simple, right? Nothing fancy. Just only one thread will execute this part. And so instead of this, if you would have just written here OMP pragma master, we don't need to check the condition if ID equal to 0. It is doing the same thing. Basically implementing same logic with pragma of OpenMP. Clear? Another construct is single. Single means it is similar to master, but you are not forcing that only master thread should execute this part. Any thread should execute this part, but only one thread should execute this part. Not all. Suppose you are allowing any thread. Suppose thread 1 enters here. All other threads, including 0, will be skipping this and waiting at this point. Okay. So there is implicit barrier at the end of this implicitly. So even if you do not use this barrier at this point, they are having anyway barrier at this point implicitly. But unlike this, master doesn't have barrier here. Other threads can actually execute the other portion of code. So in this case, if given a choice that whether should you use master or single, what would you use?
We will be using single for the case when there are many shared data items among the threads, right?
As in, can you repeat?
See, if we will be using single in the situation when there are many, I tell you, many shared data items, we can use it, no?
Yes, we can use it. So I'm just saying master versus shared, the difference. Master means only master thread will enter
Only
that block.
master thread, yes, can enter.
And single means any thread can enter, but only one thread can enter.
Okay.
If thread three enters, okay,
So
other thread will
if multiple threads are sharing a common data item, then that common data item can be updated within this function exchange boundary.
But only when you want only one thread to update that. So in this case,
only one thread to update, yes, at a time.
Yeah, yes, not at a time, only once, not at a time.
So it's not dynamic.
It is only once. So this block will get it is only once, not multiple times. So it is not like that one thread enters, it comes out, other thread enters, comes out. No, for that we have critical. Single means you want only one thread to execute only once. You don't want that portion to be executed again by any other thread.
Okay. So for critical section implement, you have a separate construct critical.
Yes. Critical is critical for all threads. Is for only single thread.
Okay.
So basically we would have used master construct here, because single, if you use a single, it would have also done the job, but it would have introduced the barrier at this point, because simple introduced the single introduced barrier, master doesn't. So we would have used OpenMP master instead of if ID equal to 0 in our Pi example. Clear? And if you want to simulate the behavior of single to master by not forcing threads to wait, you can add no wait construct also with single. So pragma OMP single, no wait. So only single thread will enter and other thread will not wait. They will just continue. They will not wait at the barrier at the end of single thread. Is it clear or slightly confusing? We can spend some more time to clarify if there are any doubts.
Sir, one thing is that if they have chosen the default behavior, there must be some reason, right? So in real world scenario, when will I use something as master or single, sir?
So master, you have already the use case of Pi. If you want only one thread to update something, basically some variables which kind of just flags, right? So whether the race started or not. Okay, they started. For example, suppose you want to simulate the race ends and who wins. Right? The thread who reaches certain point first is the winner. So suppose you created 10 threads here, but 8th thread reached this point first, right? So he wants to keep the mark that okay, I reached first. So you use single and allow only one thread to update that, and then other thread will just wait here.
Okay, okay,
Where
got it.
master will like it only zero thread can enter here, not no any other thread can enter here. So wherever you want to say find out a winner in any dummy example, or you want to keep track of what was the earliest point one thread finished, you can maintain using single.
So then
And no
one
other
example I would
thread.
like to give here, sir, that if we use
Mhm.
single and let's suppose this can help us to figure out what architecture style shall we using, like what kind of scheduling policy. If we see thread one comes very fast, then thread two takes a lot of time. So we can use that to make a good scheduling policy, right?
Correct. Very good point, and that can really be implemented, and it will be insightful. Good use case for single. So
Okay, sir.
if always a certain thread is finishing for earlier, it will have its mark on say thread ID 0 finishes faster than other. Yes. So yeah, so these are the simple concepts, and now we will jump into sections. So basically, what I was trying to convey: parallel for loops, OpenMP sections. In middle, we discussed these barriers and uh, single and master. So it's very simple construct, similar to parallel for. These are independent executions, and after entering the sections, every thread will pick one uh, section from this and execute them in parallel. And these are independent tasks basically. So here, three threads will be picking one function, and they will be running. And by default, once you reach the end of these sections, you have implicit barrier. Just like similar parallel for, all threads will wait at this point of sections construct. Simple, nothing fancy. But they may have very vast range of use cases in all practical applications where you don't have something structured kind of for loops or something, but you have task parallelism where you have some DAG of dependencies where task A and B can go in parallel, but task C can be only executed after B and C finishes. So you just create sections for A and B, wait at the join, execute C, and then so on. So you can design any DAG using parallel sections. So something like that. Suppose you have A, B, you create sections, then you execute C, then you create another section with multiple things going in parallel. You may have another independent section going on independently, which waits for this. So you can design any kind of execution path with sections and section. Clear? Not giving an example of this because they are very basic constructs and can be understood easily. If you have questions, we can answer. Okay, I assume there are no questions. Another powerful construct similar to sections, is tasks. So same as we have OMP parallel, we can define a task where after that, whatever is the function, multiple kind of uh, threads will be executing this task too. And there's a barrier. All tasks will be uh, waiting here. And then maybe I think I should go in right flow. Suppose you create a parallel region. There are four threads running in parallel. Each of them will hit this task construct. Each of that thread will run this task, and it will wait at the barrier. Then single task get created because there is a single construct, and bar is only called once by a single task, and then it ends. So if you see, the multiple foo tasks will be created by one thread, by each thread. From this, all foo will be finished by this barrier. So control will not go beyond this till you hit the barrier. Then after all thread finish, there's a single clause, just we discussed, right? Only one thread will enter here. It will see the task stuff. Only one thread will execute this, and then all thread will wait at the bar point and finish. Any questions? So silent means either not understood or fully understood.
Sir, in this case, inside the single, we don't actually need to use task, right? I mean, it would have worked regardless. Sir, I couldn't hear you. Hello? I'm not audible, sir.
Sir, you are not audible, sir. No, sir, not audible.
Aurab, you can deliver the link. Yeah.
Okay, good.
Now it's audible, sir.
Yes, good. Yeah. Now repeat the question.
Yeah, I was saying inside this OMP single, even if we don't write OMP task, like the effect would be same, right?
Effect would be same, yes, but
Because
there are
only
some,
one thread will execute it.
yeah, but conceptually there are some differences between task and just a set of instructions. So I'll cover that in next slide. So this is not always true that you can just replace the uh, single pragma by single without using task. That is not true. So task has some meaning, that it creates the context of the data and instructions you want to run, and then it, maybe I'll just give an example. So instead of
Okay.
spending too much time on this, so everyone knows Fibonacci series, right? Where we have f of n equal to f of n minus 1, f of n minus 2. And a simple recursive function, if you write int Fibonacci of n, where you have x and y, if problem size is less than 2, then just return n, else Fibonacci of 1, Fibonacci of 2, and finally x plus 1. Correct? So for now, just ignore this task and see whether you understood the Fibonacci operation. So there are recursive calls to same function. Correct? So,
Yes,
so how this will work? So you call this function, whatever n equal to 4. So you have xy, you hit this task 1, and you start Fibonacci of 3, 4 minus 1, and it will start its execution in parallel. And the control will go to next one, because there is no barrier here. It will invoke Fibonacci of 2, y equal to 2. So now two threads are running in parallel without any synchronization. And now you are saying OMP task wait. So all tasks will wait at this point, and finally you are doing x plus 1. Okay. So now once this Fibonacci of 3 will go to recursively this will again go inside this function. It will create another fork of 2. So it will be recursive calls of different Fibonacci numbers. So initially you start with 0, then you have 2 forked from first call, then second 2 from second, third 2 from third, and so on. So you can create a recursive tree of parallel execution. So at a time, all 4 branches can run in parallel using task. Okay. So when you create a number of tasks, OpenMP can either start the task mm, uh, when it got the call request for the execution, or it can delay. So there's no guarantee that after this execution you will start immediately this execution. You may not. That is dependent on operating system. Sorry, OpenMP runtime. But you define this task that way. You get parallelism without uh, doing much of synchronization among threads. Okay. So yeah, now is it clear? Clearer than the previous slide? How tasks are defined?
Sure.
Okay. So now if you remember uh, very first slide when I mentioned to you that whenever we use OMP Pragma, whatever defined before that are by default shared when you use them, right? In all OMP parallel stuff. Uh, but unlike that, in OMP task, when you say int xy, although they are part of the scope of master thread, x and y are by default private here. Okay. So there is a problem with this. Even if you run this program, when you try to add these things, it will just use the default value. So in this case of garbage, and this value which is written by this Fibonacci of 3 or 2 will not reflect as an answer. So we need to ensure that the values from these calls should be reflected in the output. So to do that, we add shared specifier to ensure that treat that x as a shared variable. By forcing it to be shared, by default it's private. Similarly y, and then you say whenever you wait till this point, you have the values from x and y to be shared and updated as part of your function call, and then you add it. So this is the end-to-end execution of OMP task with shared x and y, and forcing it the task to wait here because you want x and y to be calculated. If you let the thread exit that part, so you don't have the control of both values together. So that's how the the OMP tasks work. So yeah, so these are the OpenMP tasks construct and open for discussion for these tasks and related
One
stuff.
question over here, sir. What if we don't write Pragma OMP task in both the sections and we just wrap this into Pragma OMP parallel? Will there be any difference?
Will there be any difference?
Like in the very beginning slide which you taught, right? Pragma OMP
Yeah,
parallel.
yeah. So what it will do, it will Fibonacci of n-1, Fibonacci n-2, it will call recursively. The difference between these two will be, so if you use parallel, uh, you will always execute Fibonacci of n-2 after n-1. Suppose you got my point, what I'm saying, trying to say. Okay, let me see.
It went straight up from my head.
Okay. So suppose you wrap this thing in parallel. Instead of task, I'm saying parallel. Okay. Assume this is a parallel, whatever I draw. And you call this Fibonacci of n-1, Fibonacci of n-2. So what will happen? Uh, you will have multiple threads entering into this and executing same values of n-1, n-2 redundantly. Correct? So
Yes.
you won't get the uh, parallelism. You will be calculating Fibonacci of n redundantly by multiple threads.
Okay.
I still can hear some question marks. So let me see if I can help you with that. Okay, so this is my parallel for, just for example, okay. So if I call x equal to fib of, so say n minus 1 in this case, y of fib of n minus 2, and suppose you have specified number of threads are 4. So this means this portion of code, every thread will execute the same example which we printed printf multiple times.
Oh, okay. Same thing will be executed 4 times.
So
Uh,
same as printfs. So
got
fib
it.
of 3, fib of 2, fib of 3, fib of 2 by all threads. We're using same computation redundantly. So you are not achieving parallelism. What you want these two to be different branches of parallel. X should go independently, Y should go independently. Right?
Got it,
So
Sanjay.
that can be achieved using this construct. So you hit task, you create a fork of X, you create a fork of Y, and when you finish both X and Y finish, then you compute what is X plus Y. So this is the purpose of task, not same as parallel construct.
Thank you, sir.
Yeah. So hope this is clear now, right?
Yes, sir. Yes, clear.
So yeah, that's what I had in my mind to discuss. So as a high-level summary, what all we have discussed, we started with parallel regions with simple shared private variables, their scope, barriers implicit, the way to fetch threads by APIs, and then we discuss critical, atomic, single, master, and then for loop with reduction, scheduling, uh, sections, and tasks. So this is an overview of popular and basic constructs of OpenMP. And OpenMP is very vast. Uh, if you found enough interest in these 2 hours, the world is open to explore many constructs, interesting constructs to OpenMP, and start your journey of parallel programming with OpenMP. So at this note, I would like to stop, and thank you everyone for listening to OpenMP, and feel free to contact me if you have any pointers or any doubts to my email ID. I would like to answer those. Yeah, I would like to take any questions if anyone has now. Okay, so if there are no questions, I can conclude today's second lecture of OpenMP. I hope everyone learned something out of it.
Yes, sir.
Sir, libraries like NumPy, BLAST, these all scientific computing libraries, do they use same OpenMP construct inside?
Yes. So NumPy and all they use C++ OpenMP. And again, whenever there is some need of critical implementation where constructs are not available or not optimal, they are also used in pthreads and low level threading. But OpenMP is popular among all these libraries which are there in Python.
Okay. Okay, sir.
So if you know OpenMP, you can actually write efficient NumPy libraries.
Oh, that's great to hear. Good
Yes.
motivation to learn.
Yes. OpenMP is important and popular everywhere, and also simple.
I could see it's like a lot of composition, right? Like you're composing things.
Yes. So they are actually ready-made constructs, so you can configure them for your use, and it is written in such a way that popular constructs, popular design patterns are covered for parallel programming. If they are not covered, then anyway, pthread is there. You can always write complex code. Pthread is a Bible. You can write anything with that.
Thanks a lot, sir.
Yeah. Thank you. So, Praveen, can we stop?
Sir, what is the difference between CPU bounded task versus IO bounded task?
Okay, good question. CPU bounded task means when you have, for example, the pi calculation, right? You are not,
Yeah.
you are just running computation one after another. You are not reading something from memory to compute that, right? So if you have say 1,000 threads, your pi program will more or less scale in similar order of your number of threads. So you may get 1,000x speed up if you have 1,000 threads. But in the case of IO bound task, your computation needs the data from memory. So for example, you want to calculate the average of array, right? The example which we saw. So in that case, the thread will be reading data from the array, which will get completely copied from main memory to RAM, L1, L2, and so on. So that even if you create 1,000 threads, the speed at which the memory controller feeds data to caches, that is bounded by the bandwidth of memory. So even if you have 1,000 tasks and the all 1,000 tasks collectively are asking for say 100 Gbps of bandwidth, so 100 GB is getting read by all across all threads, but your memory bandwidth is only suppose 20 Gbps. So your speed up will be bounded by those 20 Gbps. So you may not able to use those 1,000 threads even if you have those. So applications which are such memory bound means that memory intensive, which are using more memory, so they are called as memory bound. And those who are not, they are more compute intensive, they're called as compute intensive. I don't know whether I defined it correctly, but
Yeah.
the idea is that.
And suppose we have a function which uses both of the things. So, how can we optimize that function?
So, so then uh, once you enter into the level that you want to write a performant code, then you need to actually first understand whether it is giving us some opportunity to optimize or not. So yes, so there are standard practices where you calculate the requirement of applications in terms of how much memory you need and how much number of instructions you are executing in certain amount of time. So then there becomes a graph. So you can actually go and read about what it called as arithmetic intensity of an application. So remember the term arithmetic intensity. So it's like a pen and paper work around to analyze the nature of your application, whether it's a memory bound or whether it's a kind of compute bound. So the graph flattens after some point. That the graph of arithmetic intensity. So if you are lying before it flattens, then you are compute intensive. If it is flattened, if you reach after flattening it, it is memory intensive. So I don't know whether I give correct answer, but if you read on this term, arithmetic intensity, you will find literature on that.
Okay, sir. Okay, thank you.
Sir, one last question.
Yeah.
Does OpenMP support programming in GPU?
OpenMP doesn't support directly programming into GPU, but I might be wrong because OpenCL has many constructs which are GPU friendly. So there is something
Okay.
similar to OpenMP. There is OpenCL.
Okay.
OpenCL has similar construct
Mhm.
which converts your code into GPU friendly one.
Okay.
So OpenMP directly doesn't have support for GPUs.
Sir, is memory and IO intensive are same or?
Memory and IO intensive, you can say more or less same. Yes.
Okay.
So IO actually is a broader term than memory. IO also covers memory bandwidth, also disk bandwidth. Suppose your program is using file system, so data read by file system is slower than data read from memory. So IO intensity also includes memory as well as file IOs, where memory is typically referred to the main memory and caches.
Okay. So IO intensive application will be even slower than memory intensive.
Yes.
Okay. Okay.
Okay, Saurabh,
Yeah. So if no further
thanks.
questions, we can stop.
Any more questions? If no,
Good.
Thank you. Thank you very much.
Thank you so much, everyone, for attending, and enjoy the remaining sections of the course.
Thanks a lot, sir. Thanks a lot.
Bye.